Hi folks, today we're going to talk about poles and zeros in the Laplace transform, and I'm going to use this PowerPoint and let's see if it works. So the idea is, we've been looking at different time functions and their Laplace transforms, and here is kind of a list of the kinds of things we've been looking at. So these are, if you remember, we had e to the minus 2t, and the Laplace transform for that was 1 over s plus 2, with the region of convergence being sigma greater than minus 2. And if we took e to the 2t u of t, then the Laplace transform was 1 over s minus 2, and the region of convergence was sigma greater than 2, and so on. And then we had these particular ones where we had two exponentials. And if you look at the third one from the bottom, that's 2e to the minus 3t u of t minus e to the minus 2t u of minus t. And for that, we got a region of convergence that was between minus 3 and minus 2. So let's take a look at these and notice something. The first couple are right-sided. That is, the time function is non-zero to the right of a point, which in this case is 0. So for t greater than 0, we have a non-zero value. For t less than 0, we have 0. And in the case of the third, minus e to the minus 2t u of minus t, that's left-sided. The function is non-zero to the left of the point t equals 0. And then if the third from the bottom is a two-sided function, we have e to the minus 3t u of t, which is non-zero for t greater than 0, and then we have e to the minus t u of minus t, which is non-zero for t less than 0. And so that's a two-sided function. It has values both for t greater than 0 and for t less than 0. And that's the same thing for the last thing, which was e to the minus 2 times absolute value of t. That also has values both for t greater than 0 and t less than 0. And you'll notice that if you have a right-sided function, you end up with a region of convergence which is to the right of a boundary. So the first one is right-sided, the region of convergence is to the right. So is the second one. The third function is a left-sided function, and the region of convergence is to the left of a boundary. And the fourth one is right-sided, the region of convergence is to the right. When you get a two-sided function, you get a region of convergence which is between two boundaries, in this case between sigma equals minus 3 and sigma equals minus 2. And that's because 2e to the minus 3t u of t was a right-sided function, so its region of convergence was for t greater than 0, or was to the right of sigma equals minus 3, and e to the minus 2t u of minus t was a left-sided function, so its region of convergence was to the left of minus 2, and when we take the intersection of those two regions, we get the region between minus 3 and minus 2. And then again, the right-sided function will have an ROC to the right, and a two-sided function will have an ROC between two values. So the other thing, notice that all of these Laplace transforms are of the form where we have a numerator polynomial divided by denominator polynomial. Now that's not the case all the time. We're going to have situations where we won't just have a polynomial at the top and the polynomial at the bottom, and I'll show you one of them in just a little bit. But for the most part, this is the form that we will have. We have a polynomial at the top divided by a polynomial at the bottom. And this is, if I have a polynomial in S, I can always factor it out so that I have the roots, I have a product of terms. And in this case, I'm writing them as s minus z sub I in the numerator and s minus p sub I in the denominator, because the roots of the numerator polynomial are called the zeros of the system. And you can see why. If I plug in s equals z1, for example, in the top I get a factor which is z1 minus z1, which is 0. And if 0 is multiplied by anything, you still get 0. So at any of the zeros of the function, as z1, z2 all the way up to zm, you'll get the function will go to 0. And in the poles of the system, when s takes on the value p1, p2, or all the way up to pn, any of these values will result in a 0 in the denominator, which means that x of s will go to infinity at these values. So x of s goes to 0 at the zeros of the system, and it goes to infinity at the poles of the system. And by definition, then, we can't have a pole in the region of convergence, right? As soon as we have a pole, that means that the function is blown up, has gone to infinity, and therefore that can't be the region of convergence. Okay, so are there functions that have regions of convergence that are the entire S-plane? And the answer is yes, there are. And we kind of saw one last time, but let me show you again. And suppose I have the one that I had last time was x of t equals u of t minus u of t minus 1. So let's make it a little bit different, call it u of t minus 2. And let's try and see if we can get this to focus. Okay, there we go. So if my head goes away. If I take this and I take the integral, if I take the Laplace transform of this, x of s is equal to the integral from minus infinity to infinity, x of t e to the minus st dt, or let me just go all the way to here. Yeah, this is much better. And this can be written as integral from 0 to 2 of, in this region, x is just 1, so this is just e to the minus st dt, and that's going to be equal to minus 1 over s, e to the minus st evaluated between 0 and 2, and then if I plug those in, I get minus 1 over s e to the minus 2t minus minus 2s and minus e to the power 0, or that's 1 over s 1 minus e to the minus 2s. And this thing does not have a polar 0. So notice that this is, when I said there are some times when we won't have a polynomial over a polynomial form, this is what I was talking about. Sometimes we'll end up with these exponentials generally in the numerator. And in this case, it looks like we have we do have a polynomial on the bottom, but it's not of the form n of s over d of s, and this is no longer a pole because at the value, at the root of this function doesn't blow up, right? So if I evaluate that at s equals 0, I get 1 minus e to the power 0 over 0, which is a 0 over 0 form, and so that's not infinity yet. I can use L'Hopital's rule, and if I take the derivative of the top, I get 2 e to the minus 2s, and at the denominator, I just get 1. Evaluate that at s equals 0, and that gives me 2. So that doesn't blow up, and therefore s equals 0 is not a pole. Okay, so this particular function is something that has a region of convergence that is the entire S-plane. Okay, so the poles and zeros characterize the system itself. So that's the nice thing about the poles and zeros. If I know the poles and zeros, I know a lot about the system. Okay, first of all, remember that the poles are defining the boundaries of the region of convergence. So if I have a pole to the right of the j omega axis, and my function is right-sided, if I have a causal impulse response, for example, the causal impulse response will be right-sided, right? H of t will have non-zero values for t greater than 0. It'll be a right-sided function. That means that the region of convergence will be to the right of a boundary. That boundary is defined by the pole. You can't have a pole in the region of convergence. So if I have a region of convergence which is to the right of a boundary, then I better not have a pole to the right of that boundary, because then otherwise it's not a region of convergence, right? So I can't have a pole on the right side of the S-plane. Yeah, so if I have a pole on the right side of the S-plane, I can look at it and say, if this is a causal system, it's an unstable system, right? In order for a causal system to have a stable response, the pole has to be to the left of the j omega axis. Does that make sense? Let's try it out. So suppose I have something which has a pole here, right? That means, and it's single pole, so I'm just going to look at this. So that means that's the boundary of my region of convergence. If my function is right-sided, then my region of convergence will look like this, will be to the right of a boundary. It won't include the j omega axis, and therefore it won't have a Fourier transform. And if this is an impulse response, then the system won't be stable. If I have a right-sided function, the only way the j omega axis will be part of the region of convergence is if the pole, the rightmost pole that I have, is to the left of the j omega axis. I could have poles over here, and that's fine, but if it's a right-sided function, if I have a pole here, that automatically then blocks my region of convergence. My region of convergence can't go over that pole. It has to then lie between these poles, these boundaries, which would mean that I have a two-sided response, which is no longer right-sided. For a causal system, I have to have a right-sided response. That means the last pole on the right has to be to the left of the j omega axis. By just looking at the pole, I can tell you whether the system is, if the system is causal, whether the system is stable or not. Okay, so that's one thing. Let me see if... So here's the... Here are basically the rules. If x of t is right-sided, the region of convergence is to the right of a boundary. If x of t is left-sided, the region of convergence is to the left of a boundary. If x of t is two-sided, the region of convergence is a strip bounded on both sides. And the region of convergence cannot contain any poles. And if x of t is a finite duration and is absolutely integrable, then the region of convergence is the entire plane. Okay, so those are the rules. Okay, so let's take these poles and do something else with it. Let's try to figure out what the transfer function of a system is by just get an idea about the transfer function of a system by just looking at the poles. Okay, so here is a function, and we know what we have x of t equals e to the minus t u of t. And for that, we have a Laplace transform is 1 over s plus 1. The region of convergence is sigma greater than minus 1. And to find the transfer function, what I have to do is I have to evaluate this on the j omega axis. Now, what I'm going to do is I'll go up and down the j omega axis, and then I'll take a look at what happens. Notice the pole here is at minus 1. So I can rewrite this as s equals minus, x of s equals 1 over s minus minus 1. And the reason I did this was to show you that, if I'm looking at the magnitude of x of s, then the magnitude of x of s will just be 1 divided by the distance from wherever I am to the point minus 1. Okay, so, and if I want the transfer function of this, I need to travel up and down this, the j omega axis, right? As I move up and down the j omega axis, I'm going to try and see what the distance is at whatever point I'm at and the pole, and that's going to determine what my transfer function looks like. So what I did here in this figure is on the right, I've actually plotted the transfer function. And on the left, I've plotted, where I am on the j omega axis. Ignore this one. This one has 2 points. Don't ignore this one. This one has 2 points. So the point below and the point above, so the point at omega equals -3 and omega equals -4 and omega equals -2, I think, is the distances are then plotted. The transfer function is then plotted on the right. So let's see if I can do this. So now let's just move up the j omega axis. As I move up the j omega axis, I can see what happens to the transfer function. I come closer. Notice here I'm the closest to the pole. I'm at omega equals 0, which is the closest to the pole. So I have the largest value of the transfer function, because the transfer function is 1 divided by the distance of omega from the pole. Right, so here we go. And then as I go above, I go the other way. Right. So we can use this idea to design filters. Here's one where I have a 2-pole filter. And what that 2-pole does is, as long as I am closer to one of the poles, as soon as I get close to one of the poles, that means the denominator has gotten smaller and the magnitude will go bigger. And then as I move away from that pole, the denominator will again get larger and the magnitude will get smaller. If I place the poles properly, if I do a nice job of placing the poles, I can keep the magnitude more or less constant. And this is one of those cases where I've placed the pole at -200 plus and minus 250 on the omega axis. So the pole is -200 plus J250 and -200 plus J250. And let's take a look at what happens when you look at the transfer function of the system. So that's what it is. And here's the transfer function. It's a nice low-pass filter. I've broadened out the peak. Now, suppose I didn't want to broaden out the peak. Suppose I just wanted to block one of the frequencies. Say I wanted to block the DC component of the signal, right? So the way I can block the DC component is I can put a 0 at omega equals 0, because remember that the transfer function goes to 0 at the zeros. So if I put a 0 at omega equals 0, then the function will go to 0 at that point. One more thing. Notice that because we're restricted to lie on the j omega axis, we can never actually hit any of the poles. Okay? We can come close to the pole and we can move away from the pole, but the poles, the way that we have set up here, the poles are all off the j omega axis, so we can never go to infinity in this case, right? So now if I wanted to make this get rid of a particular frequency, what I can do is I can take that, I can put a 0 at the origin. Now if I put a 0 at the origin for this particular set of poles and this 0, look, the way I put a 0 at the origin is I put an S in the numerator, and that means that I have a 0 at the origin, right? And if I plot this, this is what I get. Now I can reduce the effect of that 0 if I move away from the origin. So this one is sitting at the origin, so omega will hit that 0, and at that point the transfer function will go to 0. If I don't want the transfer function to go to 0 at that point, I just want some attenuation. I just want the DC component to be attenuated a bit, brought down a bit. Then what I can do is I can take that 0 and I can move it away from the axis, so I never actually hit the 0. So I can do something like this. I can take that and I can move that 0 off. And if I move that 0 off, here is what I get. Notice that it no longer goes to 0 as 0, it just kind of goes down as 0. Okay, so here's what we've learned. That the Laplace transform, most of the functions that we're interested in are ratios of polynomial in S. The roots of the numerator polynomial are called the zeros of the system. The roots of the denominator polynomial are called the poles of the system. And the region of convergence is bounded by vertical lines through the poles and possibly infinity. And the poles and zeros can tell us a lot about the frequency response to these systems. And I'll show you a few more examples at some point, but you can, by judicious placement of the poles and zeros, we can design different kinds of filters. Okay, so that's all for today, folks.